In this video, I will elaborate on section 4, which covers first law of thermodynamics, 4 basic thermodynamic processes, and cyclic processes. The state of an ideal gas is defined by the equation of state, PV equal to nRT or PV equal to nKT. There are 4 variables, namely P, V, N, and T. The 4th variable is defined once we know any 3 of these variables. In other words, the state of the ideal gas is well defined once you specify any 3 of the above variables. The PV diagram is also known as the indicator diagram. The area under the PV graph represents the amount of work done on the gas by an external force. The work done by an external force to displace a piston by an amount X is given by the area under the force against displacement graph. So work done equal to integration F dx. So F divided by A and dx multiplied by A will give us P dV. So it's the same as the area under the PV graph. Okay, next I'd like to talk about positive and negative work done by the external force. Consider the work done by the external force F on the gas in figure 1. Figure 1 shows the diagram of a gas inside a cylinder. Work done by the external force is positive when the direction of the displacement by the piston is the same as the direction of force when the gas is compressed. Similarly, work done by the external force is negative when the direction of the displacement by the piston is opposite to the direction of the force. So in summary, W is the work done on the gas by an external force. W is positive when the volume of the gas decreases, and W is negative when the volume of the gas increases. So consider the PV diagram on the right. W is positive when the gas is compressed from state B to A. W is negative when the gas expands from A to B. First law of thermodynamics. Okay, recall that the internal energy is the summation of microscopic kinetic energy due to random motion of the molecules and the microscopic potential energy due to intermolecular forces. The microscopic potential energy of an ideal gas is 0. Therefore, the internal energy of an ideal gas refers to its microscopic kinetic energy due to random motion of the molecules. Recall that the kinetic energy of an ideal gas molecule is 32 kT. Hence, the internal energy is proportional to the thermodynamic temperature of the gas. In equation form, the first law of thermodynamics is delta U equal to Q plus W. In word form, the first law of thermodynamics states that the increase in the internal energy of a system is the sum of the heat supplied to the system and the work done on the system. Note that delta U is the increase in the internal energy of the system. It is not the change in internal energy. So this is a very important point. I would like you to take note. Also, delta U can be positive or negative. So when we say the increase in the internal energy is positive, that means that the internal energy is becoming larger. When we say the increase in the internal energy is negative, what we mean is that the internal energy becomes less. Okay, this table is very important. You should study it carefully. Next, we talk about 4 basic thermodynamic processes. The processes are isothermal, isovolumetric, adiabatic, and isobaric. These 4 processes are important for A level because they are the only ones that can be treated quantitatively. So there'll be lots of calculation for this kind of processes. Other processes will be very difficult to calculate. First, talk about isothermal process. Isothermal means constant temperature. Now remember, when the temperature is constant, delta U is 0. Means there is no increase in the internal energy because temperature is constant. Remember that internal energy is proportional to temperature. So when temperature don't change, internal energy also do not change. So delta U becomes 0. So by the first law of thermodynamics, Q will be equal to minus W. Next, we talk about isovolumetric process. means constant volume. So it's given by this straight line, vertical line from I to F. So for isovolumetric, the volume does not change. Therefore, the work done is 0. In this case, delta U will be equal to Q. Q is the heat supplied to the system. Adiabatic process. Adiabatic refers to the situation when there is no heat transfer to the system. In practice, if a system is well insulated, then you will not have any transfer of thermal energy. So Q will be 0. So in this process, delta U will be equal to W. Isobaric process or constant pressure process. For a constant pressure process, the work done can be calculated very easily because the area under graph is a rectangle. So the work done is minus P delta V. Okay, note the negative sign. So which means that if delta V is positive, that means that the gas expands, then W will be negative. If delta V is negative, so that means that the final volume is smaller than the initial volume. So delta V itself will be negative. So negative multiplied by negative, you get positive. So which means that the work done will be positive when the gas is compressed. Next, we look at cyclic processes. A cyclic process means that the state come back to the original state. So for example, in the PV diagram, from state 1 to state 2, you go via A, and then after that, you return via B. So in this case, when you return back to the original state, the internal energy remains the same. So there's no increase in the internal energy. So delta U will be equal to 0. So for cyclic processes, delta U is 0. So once delta U is 0, Q will be equal to minus W. And the work done is given by the area enclosed. So in this example, when we move from state 1 to state 2 via A, the work done by the external force will be the area under the blue line, which is the A. And when you return, the area under the graph is under the red dotted line by process B. So from 1 to 2 via A, the work done is negative. From 2 to 1 via B, the work done is positive. And the area under A is larger, so therefore the net work is negative. So we say that W is negative for clockwise cyclic process and W is positive for anti-clockwise cyclic process. Okay, example 8, the work done on the gas is an expansion, so we expect it to be a negative work done. And the area under the graph, in this case, this is a trapezium, so we can calculate the area of the trapezium, so give us minus 35,000 joules. Change in internal energy. So for monoatomic ideal gas, we know that U is 32 NKT. And we also know that NKT is equal to PV. Therefore, U is equal to 32 PV. So the increase in internal energy will be 32 P final V final minus P initial V initial. So delta U is 97,500 joules. So for part C, Q is 132,500 joules. Example 9. This is a cyclic process. So delta U is 0. It is a clockwise cyclic process. So W is negative. So the area enclosed will be minus 12,000 joules. Based on the first law of thermodynamics, Q will be positive 12,000 joules. Okay, we have come to the end of section 4.